So we can do a couple, but this, actually, I think we did this one in class, didn't we? Let's do a different one. Um,
Typically, I come and I listen, but like I don't have questions.
that's fine.
I'm
Yeah,
just here to find out if I have any.
I have questions. Yeah, let's do this one. Hey, Alan, come on in. We're just looking at the system of two equations about to start. That's one of the free response. So the first thing to do is I'm not going to tell you the mirror. I guess first thing I'm not going to do is I'm not going to tell you the mirror. And so you need to determine what kind of mirror it is. That'll be important to determine the sign of the focal point. In general, that comes up a number of times on the exam, that you need to know those different kinds of mirrors and lenses and what kind of images they produce. After I do this one, I'll remind you what those 8 scenarios are. I would make flashcards and remind yourself of them. So spherical image produces an image that is 2 centimeters high, but the object is 4 centimeters high. So if the object is 4 and the image is 2, hey y'all, I need to know what kind of mirror has produced that. Well, if it's a smaller upright virtual image, upright images are always virtual. Where else? Did y'all go somewhere else? Oh, okay. That's what type of mirror? This is, it's a convex, very good. So my object is here, my mirror is here. That means that my image is right here. Sorry, give me just a second. I need to do this thing. So it's a convex mirror. That means that the focal length is going to be negative. And since I give you the center of curvature is 30 centimeters, the focal length is 1/2 of that, so it's going to be negative 15. So that's the first thing that I need to recognize, that the focal length, what it is, and is it positive or negative. The next thing that you'll need to know is what is the magnification. But since I tell you the height of the object and the height of the image, m is equal to hi over ho, that means that this magnification is equal to positive 1/2. It's 1/2 because the image is 1/2 the size of the object, and it's positive because the image is on the side opposite the object. That means it's a virtual image. So virtual images are always upright. Virtual images are always what? Upright. So upright images have a positive magnification. So now we get to the real difficult part, which is the solving this system of two equations. And that's really what this problem is about. I just want to make sure that you know how to have that mathematical tool. It's a pretty important tool. You know, come on in. So I have 1 over negative 15 equals 1 over p plus 1 over q. And then I have positive 1/2 equals negative q over p. All of them you're going to solve in basically the same way. I can give you variations of this that would have positive or negative focal lengths, but the system of two equations is going to be very similar to this. I'll cross multiply over here, so I get p equals negative 2q. Or it might be q is equal to 3p or whatever. So just solve that equation for one of the variables. Cross multiplication works well. And then I can plug that in for p. So I get negative 1 over 15 equals negative 1 over 2q plus 1 over q. I need to find a common denominator. The common denominator here is what? Not q, but 2q. All right, so 1 over 2q is the same as 2 over 2q. So I changed that fraction to have a common denominator, and then I get negative 1 over 15 is 2 minus 1, or negative 1 plus 2 over 2q, which is just 1 over 2q. So I get negative 2q. cross multiplying here, equals 15. Our Q is equal to negative 7.5. And that's what I'm looking for. I want to know what is the image distance. It's minus 7.5. That means that this distance is 7.5 centimeters behind the mirror. I'm also going to ask you to tell me, is it to the left or right of the mirror? And so virtual images and mirrors are always to the right of the mirror. Virtual images and lenses are always to the left of the lens. Okay? So that's that one. Let me remind you those four are the four scenarios for mirrors and lenses. And you really need to know these. I've given these to you in class, but you really need to know these. If you don't, make flashcards or something. So for mirrors and for lenses. Any more? For mirrors, I have four scenarios, 3 for concave, 1 for convex. There's my focal points. I can be outside the focal point, at the focal point, or inside the focal point. And for this one, it doesn't matter where you are in relation to the focal point because the focal point is in that negative space. I'm also going to, we'll come back to that actually. For lenses, similarly, I have convex lenses. These are all called convex. And then concave. These, by the way, for mirrors, these are called concave. And then these are convex. For lenses, I can be outside the focal point, at the focal point, or inside the focal point. And for the concave lens, it doesn't matter where I am with regards to the focal point. So those are all my objects. I'll do the images in red. Here, this is an inverted real image. Here I get no image at all. Remember, because those rays are going to be parallel to one another, so it doesn't form an image. Here I get an image that is virtual, upright, and big. And here I get an image that's virtual, upright. Virtual images are always what? Upright. Real images are always inverted and small. Okay? All these words I can just take and put over here. All the words in red are exactly the same over here. An inverted real image, no image, inverted real image, no image, virtual, upright, big over here, and then virtual, upright, small right here. So if you learn one set, then the other set is exactly the same. Okay? Also, just be very careful that notice the words change. When I go from concave mirrors, that's the same as a convex lens. Both of those are converging devices. That's why they treat things, why they treat light the same, because they both cause light to converge. And these are both diverging devices. A convex mirror is diverging. A concave lens is diverging. Converging devices have a positive focal length. Positive focal length. Diverging devices have a negative focal length. There are several questions, or I don't know, a couple of questions where I just ask you, hey, what kind of image does this device form, this lens or mirror? And you just need to know these in order to answer that correctly. But then there are also questions where you're using the lens equation or the mirror equation, or like in the free response, where you have to know what kind of lens or mirror has produced that image. And in order to know that, you need to know these. So this, if there's a most important thing to know for this exam, this is the most important thing to know, because it'll touch on probably half of the questions on the exam. Okay? Some directly, but some indirectly. If you know your ray diagrams, you'll know these better too. And also, this will help you with your ray diagrams, because you'll know what kind of image to expect. And if you know what kind of image to expect, then you know where those rays are going to cross. Okay? That help? Y'all know this, right? Y'all sort of know this? You've been getting it along the way? I hope so. I think I've stressed it enough, right? Have I stressed it? Most important, right here. It's the most important. Note cards, or put it on a sheet of paper and paste it to your mirror. Just look at it for the next couple of days. Or what else? Questions? I can just look through some of the exams. Um, you're going to have something like this, where I'm just going to, for your free response, I'm going to give you 3 media of different indices of refraction, and you'll need to tell me, you'll need to first trace the rays properly as they go through. So let's just, I don't know, we'll just, look at those indices of refraction. So first of all, I'll have my ray come up. Here I know it's going fast. Here it's going slow. So as it goes into a slower medium, remember here, these rays are going to go like that. They're going to bend away from the normal. That's going to be kind of hard to draw. I'll have it so it's easier to draw. But because I'm going slower in that next medium, oh no, that's wrong, isn't it? Never mind. Y'all were looking at me funny, so I knew it was wrong. Right, that was wrong. Y'all knew that? Yeah, okay, good. Say something. Whoa! It's gonna go like this. It's gonna bend towards the normal. Uh, it's going slow here, fast here, and so it bends in that direction. And then when it goes to a low index, it's gonna bend away from the normal. And when it goes into a higher index, it'll bend towards the normal. And then when I come back into air, it's gonna go like that. This angle up here, whatever that angle is also going to be this angle down here. That whenever I move from one medium into that same medium, then the angles are going to be the same. So if I asked you any one of these angles, this angle, you should be able to give me any of those angles using the law of refraction. N1 sine theta 1 equals N2 sine theta 2 equals N3 sine theta 3, etc., etc. If I have 4 media equal N4 sine theta 4. I want you to notice that this angle right here, for example, if this is theta 3, notice how it's related to this angle, theta 1, that N1 sine theta 1 is equal to N3 sine theta 3. So I don't even really need to know medium 2 at all. I don't have to find theta 2. I can jump ahead and figure out what theta 3 is, or I can figure out what theta 1 is. You should be able to find any one of those angles. Y'all could do that? Right now, if I gave you the question right now, you'd be fine on it. Muddle your way through it. Yeah? Yeah, okay, good. All right. Other for your spots, you need to draw your rays. I mean, we could do them all here, but do we need to do the rays? There are videos online. I can do them if y'all want. You want me to do them? No. Be prepared for the more difficult ones. It's not going to be a concave lens outside the focal point. That one's too easy for y'all because y'all are so awesome. And it's not going to be a concave mirror through the focal point. Like it's not going to be this one, and it's not going to be this one. These are just too easy. Right? So be prepared for one of those others where you have virtual rays. I want to see that you can deal with virtual rays. You're going to have, gosh, 5 or 6 just using the mirror or lens equation where you're having P and Q and you have to find F or on those, you need to be careful about the sign that you use for those. So just be careful. Make sure you know what kind of mirror you're using. So like, for example, here I see an upright virtual image of myself. If it's upright and it's bigger, that means I'm dealing with a what? Concave is right. Yeah, it's a concave mirror. So that means that I have a positive focal length. But if it was an upright smaller image, that would be a convex mirror, and it would be a negative focal length. Notice I never tell you the sign of the focal length or the sign of curvature, but you need to know it just from the situation. Also, use your clues. If this is an upright image, that means it's virtual. That means that all the positive values for the image distance those aren't possible answers. So make sure you go through. I think there might be one or more where you can just do that and get rid of all the answers except for the right one. Okay? So if you're clever, it'll be an easier exam for you. And y'all are clever, right? clever, not like in devious mean ways, but clever like you're smart. You, right? Yes, it's true. Okay. Um, Not going to do any diffraction gratings. Make sure you can describe how the rays travel through, like not just being able to draw the ray diagrams, but for like this one, what the rays do. I've had several questions like that over the past exams, and you'll certainly see that. So just be able to describe in words what the rays do. Through the focal point, parallel to the axis, through the focal point, through the center of curvature and back on itself, to the center of the mirror, following the law of reflection. And then for lenses, it was the other one that was different was, what was it? Oh, through the center of the lens, and it just goes straight. So review those rules. Y'all know how to do the double lens? That's the very first question on the test. You're not dealing with a virtual object at all, so it'll be fairly straightforward where I find this image distance, Q1, and then I find this object distance, P2, and then I use this focal length and this object distance to find Q2, and then along the way I find M1, negative Q1 over P1, M2, negative Q2 over P2, and then the total magnification, which is just the product of M1 and M2. So that's what I'm looking for, the position of the final image and the total magnification of the image. Okay? Very first question. Perfectly right. That way you just feel confident in the exam. Let's just look at this one. I'm not going to work through the whole system of equations, but let's just look at this. The object is 4 centimeters tall. The image is 2 centimeters tall, and it's upright. That means it's virtual. What kind of mirror is this? It's a convex mirror, and I know that because it's smaller and it's upright. So that means it's virtual also. So this is a convex mirror, and then I say that the focal length is -5, the magnification is 1/2, and I do that system of equations just like we did before. Y'all want to do that actually? Or y'all feel comfortable with it? Y'all are mom today, huh? Quiet? Are y'all ready? Do you feel ready? Yeah, good. If you've been preparing, you're ready. And just FYI, I worked through the exam this morning. It took me 20 minutes. Usually it takes me about 25 minutes. So in that way, maybe I was going more quickly, but maybe it's an easier exam. I hate to say that because I don't want y'all to go home and not study, because you really need to study. You need to excel on this exam. Okay? Right? Can we work through this or no? I know how to do these rays. Let's just sort of do this. If I go parallel to the axis, it goes through the focal point, but this is a diverging device. That means it's going to go through the focal point like this, whereas it'll diverge and trace back through the focal point. I can also go through the center of the lens. Usually I'd trace through the focal point parallel to the axis next, but this one gets a little hinky with that one, so I like this one better. These are the two easiest rays for lenses. Parallel to the axis, through the focal point, and then through the center of the lens. And then I know that my image is going to be right here. I can do the third ray. That's through the focal point, but it's tricky because it's up in this direction, such that if you traced it forward, it would go through the focal point. That's what it means to be through the focal point in this case. And then I go parallel to the axis, and then I trace that back, and it crosses at that point as well. I think that was it. Those were the only 3 rays that we could draw for that scenario. But yours will be similar. I mean, there's also the convex mirror, and then there's the concave lens that has the object inside of the focal point. I'm looking at the ones that have virtual rays. So that, I've already said that, but that should give you a hint as to which ray diagrams you're going to have to draw. One that produces a virtual image, and there are only 1, 2, 3, 4 that produce virtual images. It could be a lens or a mirror. This is a lens, but it could also, and I'll just tell you what it is. So it could be a convex mirror like that, or a concave mirror like that, or a convex lens like that. All four of those produce virtual images. Can we remind you what those are while we're here? Yeah. All right, so here are the focal points there, parallel to the axis, through the focal point. That is, you trace it back and it goes through the focal point. You could also do to the center of the mirror. That's probably the easiest one. And it just reflects, following the law of reflection. And then my image is right there. Those are probably the two easiest rays. Here, parallel to the axis, through the focal point to the center of the mirror, following the law of reflection. Then these trace back, giving me the image. That's the upright, bigger image. That's like when I had that big mirror and I hold it close to my face, I look bigger. Those are the two easiest rays. You could go through the focal point and parallel to the axis too. Let me just go ahead and draw that. Through the focal point, that is as if it's originating out of the focal point and then parallel to the axis. See, that traces back too. And then here on this one, parallel to the axis through the focal point. And then probably the other one that's easiest is just through the center of the lens. Those look parallel, it's just because I didn't draw them very well, but they do trace back to produce a bigger upright image that's virtual. All right, look back at those ray diagrams. So I've already narrowed it down to just four. But I want you to know those four. If you know those four, you know the other four too. All right? I didn't mean to tell you all that, but it slipped out. Make sure you know the eye and camera thing. Let's just look at this. For your eye, what can change? What's fixed in your eye? No, not the focal length. The image distance is fixed because the distance from the lens to the retina is fixed. That distance doesn't change. It's, a couple centimeters. But the focal length can change. So for your eye, the focal length can change. For a camera, the image distance can change. And remember with the eye, that when I'm looking at something that's really far away, when those light rays come into your eye, they focus at the focal point. So when I'm looking at something far away, my lens is thin, it's stretched, taut, and that focal length is big. It's as big as it can get, which puts the focal point at the retina. But when I'm looking at something close, that lens has to get wider in the middle. Oh, I didn't mean to draw the eyeball wider. But the lens gets wider, the eyeball is still the same, so that your focal point is here and here. And now my object is here, and my image is there. Okay, so the image is no longer at the focal point. Look, if I draw my rays here, parallel to the axis through the focal point, parallel to the axis, they meet back there at the retina. But notice that the focal point is not at the retina anymore. I've had to shorten my focal length by squeezing that lens down. That's why you can't see close up as you get older, why you need reading glasses, because that lens is just, it grows less flexible. All right? What else, y'all? Have any particular questions? Just sort of scan through these. So you know the electromagnetic spectrum, we'll look at exam 3. Know how to do, you'll have one of these mirror problems. Have we already done this? Oh, that was for the quiz, wasn't it? Not for the quiz? Yeah, that was for the quiz. We did it for the quiz. So you'll have one of those. You're going to have stuff about fiber optics. Remember, for fiber optics or for total internal reflection, the high index is on the inside or outside? It's on the inside. Fiber optics are like glass or plastic, and then they're just surrounded by air. So high index on the inside, low index on the outside. If it's reversed, you cannot have total internal reflection. Be able to calculate that critical angle, it's just like we did here, it's just using the law of refraction with theta 2 being 90 degrees. Make sure you know the different people and why they say light is what it is. Newton, particle, reflection. Huygens, wave, refraction. Young, wave, interference. And then Einstein said it was a particle because of yeah, the photoelectric effect. Thank you. And now today we say that light is both. Or you say that in quantum mechanics or quantum physics or quantum chemistry, which you'll take, that you say that that light is both a wave and a particle. It depends on how you observe it. Okay, it's the duality of. Um, Unless y'all have questions, we'll stop. You feel okay? All right, let's start. Let me get your names for you.